All right, welcome everybody. So this is the last talk slot of DevOps. So you all made it. It's sort of like last call at the pub. So these are the stalwarts hanging around to the very last minute. So I do this talk every year. Well, not every year because I haven't been here for a few years. But I do this talk every time I come to DevOps, and of course it varies because it's a talk about looking forward and what we're working on in the future. And the future is constantly changing. So the talk's a little bit different every time. So since it's been about 4 years since I've been here, I'm going to talk a little bit about the recent past, actually, a fair bit about the recent past, as well as the present and the future, rather than doing an entirely forward-looking talk. So here's a list of the features that we've delivered since I stood in this room. It's quite a list. We've been busy. Records, sealed classes, several different installments of pattern matching. Along the way, a total revamp of the switch construct. Actually, text blocks came in since I was here last as well. String templates, which are in preview now, unnamed patterns, and unnamed classes, which are in preview now. So quite a lot's been going on. And as I talked about, at the keynote, the language work that we've been doing has been a real success story for the rapid cadence because it's taught us how to break features down from these big monolithic features like generics and modules and lambdas into sort of bite-sized chunks, but still chunks that work together. So each of these features stands alone. They're useful out of the box, but they're more useful when you put them together. This is a good opportunity to sort of review how we think about evolving the language. There are sort of two extremes that we try to avoid. One extreme is not moving forward at all, because if we evolve, not at all or too slowly, then Java will slowly become irrelevant, and we don't want that, obviously. But there's also a risk of evolving too fast and jumping at the new shiny thing. That has a lot of subtle risks. It has the risk of alienating users who may have liked things the way they were, but it has a much bigger risk, which is the risk of making mistakes. And so we try to take a slow but steady approach to evolution. The size of that feature list notwithstanding, you can think of that list as being a number of aspects of the same basic concept that we've been working on and refining for the last few years. Changes at the language scale take time. Most features have a sort of three to 5 year design cycle, and that seems like a long time, but the cost of getting something in the language wrong that we have to live with forever is pretty significant. And it's always surprising to me how there's no such thing as a small language feature. Even things that seem obvious and trivial, the number of review cycles we have to go through for the specification is always more than we expect, and the number of design corner cases that we have to confront is always more than we expect. I mean, a good example of that is there's a JEP in flight for allowing statements before the super call or the this call of a constructor, which is a long-standing request for improvement, totally straightforward. We looked at the spec and said, okay, these are the paragraphs that have to change. And then it turned out that we had to go through 2 more revamps of the specification before it was done. Just because it's subtle and takes longer than you think. So even a small change isn't small. When we're thinking about evolving the language, we try to stick to some principles. The most important principle that we have for the evolution of Java is that the most important thing is reading code. Code should be readable. It should be obvious what it means because readable code is maintainable code. Readable code is the code that you can evolve. It's the code you can look at and have some confidence that it's correct. That's a very different perspective, I think, than most programmers have because most programmers are in the business of writing code. And so we constantly get asked for features that amount to, can you make writing this code faster? And sometimes people are disappointed that the answer is no, we're actually more interested in this other aspect. But as we'll see when we talk about some of the features, the two are related in an interesting way. And so often, if you get the semantics right, the boilerplate takes care of itself. there was a question at the panel session yesterday about why did it take so long to do a particular feature, and this is one that comes up a lot. And we have an approach of first do no harm. If you don't know the right answer, then don't do anything. And that has saved us from disaster more times than we can count, but you don't see it because it's a disaster that didn't happen. And so the generics that we have now are infinitely better than the generics that we could have had in Java 1.0, which would have looked something like C++ templates. We knew we needed parametric polymorphism from the beginning. That was no surprise. But we didn't know how to do it in a Java way, and thank God we didn't do it in a non-Java way. And of course, like the big test for almost anything we do is compatibility, because people have made a lifetime of investment in their understanding of how Java works and in the Java code that they've written. And if we go and do something that breaks that code or invalidates that experience, we've broken our promise and devalued people's investments. And compatibility has all these different aspects: source compatibility, binary compatibility. One of the ones that we often forget about is migration compatibility. When we did records, we thought a lot about how are we going to migrate existing classes to records, etc. So all of these things are in the background as we're thinking about evolving the language. So I'm going to do a recap of the features we've done recently. I'll start with records. You probably all have figured records out, by now, so I'm not going to say very much about them. But the way we think about records is that they are Java's version of tuples. They are nominal tuples, nominal meaning names. The class has a name, the components have a name, and we do it that way because names make code readable. A tuple of int and int is less readable than a tuple of x and y coordinate, or lat long, or first name, last name, etc. So with records, you say this class is a carrier for this state. The state description is right there in the record declaration. And then we derive the API from that state description. We derive the implementation from that state description. You can override it if you want. And a lot of people love records because, yay, no getters and setters. And that's great. We hate getters and setters too. But that wasn't the goal. The goal was for records to be a clear semantic statement of this class is this slug of data. And by making that semantic statement, we were able to eliminate the boilerplate. If we had taken a more syntax-oriented approach, like Lombok or AutoValue or various class file generators, we would have lost out on the opportunity to be making a semantic statement, and all we would have gotten was some reduced typing. So we're pretty happy with how records landed. In the wild, we've observed, as we kind of expected, most records are one-liners, which is great, but they don't have to be. They're full-blown classes. They can have methods and all of that. One of the things people don't know about records, or don't always know about records, is records are sort of down payment on an improvement to serialization. So when you deserialize a record, if it's serializable, we will pull the components out of the stream, and then rather than constructing a record object with those components, we will call the constructor of the record with those values. And so if your record enforces invariants, they will get enforced at deserialization rather than just believing whatever garbage values are in a malicious stream. So there's a lot of questions about why didn't you do it this way. So before we had records, everybody said, oh, what we want is tuples. And so why didn't we do structural tuples? Well, tuples are great in languages where the type system is already structural. But everything else we do in Java is nominal. Almost everything else we do. Arrays are not nominal. And we do that for the reason that names matter. And so something with a name where the components have names is more descriptive and less error prone than just tuple of int, int, and int. This is the same trick we played with lambdas. When we did lambdas and everyone said, what we want is structural function types because that's what we have in this other language. And we looked at it and said, well, maybe we would want that. But nominal function types, functional interfaces, fit better into how Java works. The other thing that sometimes surprises people about records is there's actually a semantic constraint that you're supposed to adhere to. The automatic members we generate do adhere to, but if you override them, you're supposed to follow them, which is, and this is specified in the contract of record.equals, which you're extending, is that if you take a record apart by calling its accessors, component accessors, and then you feed those components back to the constructor, you're supposed to get something that's equal to the thing you started with. In other words, records are just their state. Okay, so another feature we did a while ago, so I'm going to do a quick recap of is sealed classes. The sealed classes came in right after records. Sealed class allows you to limit what classes can directly extend you. So it's a generalization of finality. Finality means no one can extend me. Sealed class means only these guys can extend me. And the subtypes of a sealed class have to be explicit about, am I myself sealed, am I final, or am I going to permit extension? And there are syntactic conveniences, like if all of the permitted subtypes are declared in the same compilation unit, you don't have to explicitly list them in the permits clause. But the point of sealed classes is making a semantic statement. You're saying, a shape is a circle or a rectangle and nothing else. So that, we'll see later how that gets used by pattern matching, but also it allows libraries to expose abstract data types, but still control all the implementations. And this is something we do in the JDK all the time. So we have abstract types like method handle, which have multiple implementations, but the implementations are all private to the JDK, and we don't want people forging instances of method handles because there are strong invariants about what method handle means. And so we used other tricks for method handle when we implemented it, but this is a more direct way for a method handle to say, here's the contract, and here are the allowed implementations. And the other benefit is that this exhaustiveness is known to the switch statement, and it can give you better exhaustiveness checking when you switch over something. So these two features work together. Records and sealed types form what are called algebraic data types, which is a very expressive way for modeling data. In some languages, this is the only way you have to model data is with algebraic data types. But it's powerful enough to model all sorts of interesting hierarchies, including domain-specific hierarchies as well as general types like list and map. And so I've given this example before, but if you want to take the the canonical example from the textbook of an expression is either the sum of two expressions or the product of two expressions or the negation of an expression or a constant, you can model that as a sealed type where the leaves are records. So this code basically says an expression is one of these four things, and each of these four things has some structure. A sum has two sub-expressions, a product has two sub-expressions, a negation has one sub-expression, and constant has an integer constant. So those two features, in turn, work together with sort of the big feature arc of the last few years, which is pattern matching. Pattern matching started out very simple. So for the first installment of pattern matching, it looked like just a syntactic trick to eliminate stray casts, which had value, but is not really where most of the value is. So the concept of a pattern fuses three things that we do all the time together, which is test for a dynamic property of a target. If that test succeeds, extract something based on that test, that test having succeeded, and take whatever you extracted, bind it into a local so you can use it later. So if we're using instance of and casting, the test is if x instance of string. The conditional extraction is, okay, I can then cast it to string and then put it in a variable. Pattern matching fuses those into one operation. So a type pattern, here string s, can be used with instance of that does all three of those things at once. If it's a string, cast it to string, bind it to s. the concision is good, but it also eliminates a place for bugs to hide, because we've all made the mistake more than once probably of cutting and pasting and changing the type name at the instance of, but not at the cast, and now you have a bug. One of the subtler things about pattern matching is it's understood pretty deeply by the language that the scope of the bindings are flow-based. So ordinarily, the scope of local variables are block-based. We use curly braces to delimit the scope. But for bindings that are created by patterns, their scope is somewhat subtle. So I think, oh no, I thought I had highlights for those. But in the if I say if x instance of string s and s.length is greater than 0, the reason s is in scope after the and is the language knows you could only have gotten there if the test succeeded. Similarly, if we invert the conditional and say if not x instance of string s or s.length is less than or equal to 0, same thing. The language knows the semantics of or and knows that you could have only gotten to the part after the or if it was an instance of string. So it knows s is in scope there. And similarly, in the body of the if and else, s is not in scope in the if body, but it is in scope in the else body. So this is a little bit different from the scoping of ordinary local variables, which have what I would call rectangular scope. This is one of those things where if no one told you this, you'd probably never notice, because things just work the way they expect, because pattern bindings are in scope when they would be what we call definitely assigned, and they're not in scope when they are not definitely assigned. And the reason we had to do this, there was some controversy over this because it seems like a fairly complicated, change to how the language works. The reason we had to do this is we didn't want to be in a situation where simple refactorings like invert conditional didn't work. And so what that meant was there had to be a relationship between what was in scope in the various arms of an if and the condition. So type patterns are the simplest kind of pattern, but patterns can be much deeper than that. So records come with their own kind of pattern, which are a special case of what we call deconstruction patterns. A record pattern fuses a type test, are you this record, with conditionally extracting the components of the record. So you can say we deconstruct the record into its components. So if we have a circle record where we say record circle, center, and radius, we can ask a shape, are you a circle, with a record pattern? And if so, we're going to extract the center and radius components and bind them to center and radius. You can also use type inference here, so you can say var instead of the concrete type, and it will figure that out. Now, this rabbit hole goes kind of deep because patterns can be composed. So I can take another pattern and put it inside one of these record patterns, and things will get matched recursively. So if I have the same declaration, record point, record circle, and I say if shape instance of circle, and then in the first component I have another pattern, which is a record pattern for point, what that means is the thing a circle? If so, cast it to circle, extract the center and radius components. Now try to match the center component to that point pattern, which is, okay, is it a point? If so, cast it to point, extract the x and y, bind them to cx and cy. So either all of this succeeds at once and all the bindings are set, or the pattern match doesn't succeed. So this allows us to define data structures in a deeply nested way and still extract them in a straightforward and compositional way using the same form of composition that we do when we put it together. There's also a way, this is relatively new, there's a way to say, I don't care about this component. You can use the underscore. So in the bottom example, we're only binding cx and cy, and the underscore pattern basically matches anything and binds nothing. So we started out very simple with patterns, but there's a lot more substance to them than you might have first thought. Along the way, we had to do a complete upgrade of switch. This was such a total upgrade that a lot of people said, why don't you just give up on switch, leave it for dead, and declare a new construct called new switch? And we don't like doing that. The rehabilitation of old switch was not easy, but I think we were victorious. It was upgraded in so many dimensions. It can be expression as well as a statement. That came in Java 12. You can switch over any type, not just numbers, strings, and enums. You have a more concise and safe form of case labels, the arrow form of case labels, which only have a single consequence. That simplifies the control flow. You can use both patterns and constants as case labels. Case labels can have guards. And this is an example of we made switch more powerful by saying, you can test, is this thing an integer? So we needed a way to be able to refine what it matched. Before, all you could say was case 3. You didn't need to refine that case at all. So you can have a guard that says case integer I when I greater than 0, and that will match only positive integers. Switch was also upgraded in how it does exhaustiveness checking. It can use ceiling information or enum information for exhaustiveness. And so if a switch is sufficiently exhaustive, if you cover the cases well enough, the compiler will not require you to declare a default clause, which is great. That's less typing, right? But that's about writing code. The benefit of leaving off the default clause is not just that you don't have to type it. It's that you get better type checking from the compiler. If someone changes the assumption of a shape is a circle or a rectangle, you'll find out the next time you go to recompile that program of, your assumption's changed out from under you. What do you want to do? Whereas if you had just had a default clause there, you would have been sweeping the error under the rug and you would have gotten a nasty surprise at runtime. So as an example of exhaustiveness, which is this is a very difficult subject. We watched sort of other languages make 3 or 4 running leaps at doing exhaustiveness and said, we're going to do better than that. And then we had to make a few running leaps at it too. But fortunately, we did all our running leaps before we actually shipped something. So that wasn't imposed on users. If I have a sealed interface, say color permits red, yellow, green, I can have a switch that covers red, yellow, and green, and we know that it's exhaustive. Great. So no default is needed there. That doesn't seem very complicated. I'll show you a more complicated example, and this really isn't a very complicated example, but your heads are probably starting to hurt pretty soon with this example. I promise you that is exhaustive, but working through the details are pretty complicated. I'm not going to work through them all now, but what the compiler is doing here is it's saying, okay, well, an R can have an A and a B, an A can be a T or a U, a B can be a V or a W, and so, okay, I got the AV case covered, I got the T anything case covered. What does that leave? Well, I still haven't covered the UW case. Oh, I got that covered. Great, it's exhaustive. The compiler's going to do all that for you and tell you when you got it wrong, which is good because it's really easy to make mistakes with this. So this is when you want the compiler working for you and not against you. So if you give the compiler more information in the form of sealing information, you can be rewarded with better type checking. Static types are good. So with algebraic data types, they're great for modeling data. Same examples before. An expression is a sum, a product, a negation, or a constant. But we want to do things with expressions. And the natural way to traverse an algebraic data type is with pattern matching. So if we want to evaluate an expression, we're given an expression where an expression is defined to have four subtypes. So it makes sense that there should be 4 parts to our switch. And each of these, each of these we're going to handle one at a time. Is it a sum? If so, get the left and right sub-expressions, evaluate them, add them together. Same for product, same for negation, same for constant. And again, we get exhaustiveness. The compiler knows we've covered all the cases. So this is, pretty readable, pretty nice, pretty concise. I'm pretty happy with that. There's six different JEPs that go into being able to write this code. So when they all came along, they fit together pretty nicely. But there's a lot more to it because basically what we've done is allowed you to write visitors without all of the goop of the visitor pattern. And so if I have the same domain and I want, instead of evaluate an expression, I want to differentiate the expression, Well, so I have a method, it doesn't return a number, it returns another expression, because that's what you get when you differentiate something. Um, and for each case, well, what do? Well, you open your elementary calculus textbook. The derivative of a sum is the sum of a derivative. The derivative of a product is x dy plus y dx. The derivative of a negation is the negative of the derivative, and the derivative of a constant is 0. And so any operation that you want to perform on this domain, you can do like in this ad hoc way. It doesn't have to be part of the hierarchy. You don't have to like design what are the 72 operations I want to have on expression. Just define your domain, and then if you have more behavior you want to define on it, you can put it in the hierarchy, or you can put it in a static method wherever you think it looks good. It's a lot more flexible than the old way. Of course, you can still do it the old way, and for some things the old way is still sensible. Okay, why did we do these features? The reason we did these features is that Java really needed to up its game about data modeling. So Java has its roots in the 90s, during which object-oriented programming was all the rage. Classic OOP is about modeling complex entities and processes. And so we have all these techniques for trying to attack the complexity of modeling complex entities and processes, encapsulation and behavior traveling with state and all of that. And these are great when that's what you're implementing. So where OO really shines is in defining boundaries. And different kinds of boundaries, maintenance boundaries, version boundaries, security boundaries. And that makes sense in these big monolithic programs where you have to draw some boundaries so that you can do some sort of modular reasoning to figure out if your program is correct or not. But that's not the programming world we're really living in now. We're writing smaller services. They're interacting not necessarily with serialized Java objects, but with things like JSON or YAML. So they're more loosely coupled. They may be talking to things not written in Java. Their data may be coming in untyped forms, that don't map directly to the Java type system. And so the boundary that the language needs to help you navigate has moved. Instead of defining boundaries internally to your monolith for managing complexity, you want help from the language to define the boundary of your service so that when messy untyped or stringly typed data comes in, you have an easier way to validate it at the boundary, bind it to whatever internal domain model you want, work with it as clean, immutable, strongly typed Java data, and then do the reverse on the way out. Java 1.0 sucked at that, right? And the Java Beans pattern was a reaction to that, and that sucked too. And so it's finally time for Java to get better at that, and we took inspiration from some of the obvious places. So these features, record seal types and pattern matching, work together to make Java better at modeling pure data. Okay, so that's nice, but that's kind of backward looking. Where are we going? Historically, there was huge asymmetry in the Java APIs that we write. So when when you call the constructor of an object, that activity is aggregation. You're taking a bunch of values, feeding it to the constructor, and you're getting one thing back that's an aggregate derived from the data that you passed in. But the way you take objects apart today doesn't look anything like that. We define these ad hoc accessor methods to say, well, get me this component, get me that component, and maybe they map one-to-one with the constructor arguments, and maybe they don't. And so that means that if you have something that can be taken apart, the way we put it together and the way we take it apart are completely different. And these two activities should be they should be mirror images of each other. And to the degree that they're not mirror images of each other, that's places for bugs to hide. That's places for accidental complexity to creep in. So a lot of these features are in aid of making the object model more reversible. If you look at those record patterns, they look a little bit like constructor calls. Not an accident. We're saying, if this thing could have come about as a result of calling this constructor, what arguments would I have passed to it? That's what a record pattern is really asking. And when we call constructors, we can compose them, right? I can say, new optional of new point of, I know optional it doesn't have a public constructor, it has a factory, but you get my point. Constructors compose. And deconstruction composes now in exactly the same way. And we hope that where this is going is that the APIs that we build will be less error prone and easier to use because we won't have to design two separate, completely different APIs for doing these two mirror image operations. So, like, as an example of the composition, if I want to make an optional of shape that describes a red ball of unit radius, I can say shape.redBall of 1, that produces a shape, and then I can pass that to the optional factory, and I get an optional of that thing. And these two classes didn't know about each other, right? This is the language helping you compose things without having to arrange it ahead of time. But if we wrote a shape API today and we wanted to ask the question, are you an optional containing a red ball of radius 1, you have to write this disaster, right? And the problem with that disaster is not just that it's long, which it is, but it's error prone. And as evidence of how error prone it is, the first time I published this example, I got it wrong, right? And I didn't mean to, right? But it was a nice irony. We don't want this, right? We want to be able to say, if I'm making an optional shape this way, I want to take it apart like that. Are you an optional of a red ball of radius 1? So we want to make it possible for every constructor, factory, literal form to have a now take it apart and give me the things I gave you form. And when you have this, you get composition in both directions. And as an example of how deep this rabbit hole can go, here's an example from the API of the Java Lang class. This is the reflection mirror class. So for example, if you want to, if you have a class that represents a string array, and you want to say, what's the component type of this array class? There's a method for that, getComponentType. It has a precondition. It better be describing an array class. What happens if it doesn't? Well, it's going to fail somehow, return null, throw an exception. I don't know what. I have to decide. You have to deal with it. There's a method that you can call as a precondition. Are you an array class? Okay, good. Now I know it's safe to call getComponentType. Oh my God, why do we do this to our users, right? Why do we write APIs that are so easy to misuse? These two methods are the same method. They're the same activity. Are you an array class? If so, give me your component type. That should be one operation. We should be able to express that in the language as a instance pattern on class and invoke it maybe like this. So this is not just a convenient way to take apart data. This is I hope, a better way to look at aggregation and decomposition in the object model. Okay, so rapid fire time. I'm going to go through the features that are in preview and are coming down the pike. Probably one of the more popular features that previewed in 21 is string templates. The most frequent feature request I get from people is, can I please have string interpolation? The previous most frequent one was, can I please have local variable type inference? We gave you that, so then the request changed. You're never done. And sure, string interpolation is really convenient, but it's also really dangerous, right? I could have the XKCD comic of little Bobby tables up here, and everyone would get the joke. String interpolation is a breeding ground for cross-site scripting attacks, for SQL injection attacks. And so we'd like to be a little bit more organized about how we produce aggregates of strings from sub-expressions. Of course, the alternatives you have today suck, right? String concatenation or string.format or string builder, they all suck. So, we're not going to say just use that. Lots of languages have a feature for string interpolation. Lots of people thought we were just going to copy one of those. They never learn, do they? We looked at the problem and said, okay, well, these features are doing a useful thing, but they suck in their own ways, and we're going to do something better. Rather than looking at interpolation as the goal, we zoomed out and looked at the construction of an aggregate from fragments of text and embedded sub-expressions. So this gives us the flexibility to do a lot more than interpolation, but it also gives us the ability to do it safely. We want to incorporate validation, domain-specific analysis, domain-specific transforms into the mechanism. And this is, we didn't invent this. JavaScript has tag functions. Scala has a feature like this. And so what a string template expression looks like is a template processor, dot, and then something that looks like a string literal with embedded expressions in it. Now, when you see something dot, you should be thinking this is a method call. And it is a method call. That str to the left of the dot is a receiver. That's a public static final field of the right type. That's all it is. It's not magic. It's not special syntax. It's just a instance of template processor. And this works both with the single line string literals and with multi-line string literals. The stuff to the right of the dot is a string literal or text block that has embedded expressions, and those are delimited by escape curly brace, which is compatible with the existing syntax because escape curly brace is not currently a valid escape sequence. So no one has to go and edit their old strings in order to make it work with these. Now the cool thing is a template processor can do basically whatever it wants with the snippets of text and the embedded expressions. It doesn't even have to return a string. It can return something else. It can do validation. It can do transformation. It can declare that it throws checked exceptions that you have to deal with. And then we've included some implementations of template processor like string, and I'll show you a few more in the JDK that you can use out of the box, or you can write your own. So an example of a more sophisticated template processor is a string formatter. So this uses the same formatting sequences, the %s, %d, that string.format uses. And the trick is you have the format specifier, and that goes right before the whole. So you're saying, the next embedded expression I'm expecting is going to be a string, and I want to format it in a column of width 12 with right justification. This one happens to return a string. Like I said, they don't always have to return string, but you have a lot of flexibility to take the combination of snippets of text and embedded sub-expressions and produce whatever it is you're going to produce. A more sophisticated example, since I mentioned SQL injection, is we could have, we don't have one yet, we're working on one, a template processor for database queries, where the stuff to the right of the dot is going to be a SQL query with holes in it that we're going to interpolate into, but the template processor is going to validate that the quotes are balanced in the string literal part, and it's going to look at the embedded expressions, and it's going to escape any quotes there for proper quote hygiene, and then it's going to produce not a string, but it's actually going to make a connection to the database and produce a result set. And so what we wanted to enable was the ability for this convenient expression, which is what people often want to do with things with string interpolation, and do so safely. It also allows us to do things more efficiently. So for example, if you have a JSON API, what's really common is people will build their JSON object out of a string, concatenate a bunch of strings together, then hand that to the JSON library to parse it and get a JSON object back. If you had a template processor for JSON, you could skip the transit through string and go straight from here are all the pieces to here's the tree that the JSON API is going to produce. And so, not only does it give you more flexibility and safety, but it also may give you more performance. Okay, so another feature that we've previewed in 21 is part of what we're calling paving the on-ramp, making Java a little bit more approachable, either for beginning students or just for simple programs. Everybody loves to make fun of public static void main, and they should. It's kind of ridiculous that this is the simplest program you can write in Java. But when Java was being designed, the focus was on big programs, and these small constant overheads were considered to be, acceptable collateral damage. And generations of students have gone through the hazing process of learning these incantations. There was a great there was a great bit by one of the guests at the Java 1 keynote a few years ago where she was talking about how when she learned to program in Java, the teacher had made up a rap to remember the incantation of public static. I can't do it. But like, but she did it on stage, and like, okay, awesome for that teacher, right? That he's like taking something impenetrable and finding it a way to be, attractive to students. But really, we have to make teachers do that, right? So, this is something that makes people think Java is hard. And the reason it's hard is it's putting all of these concepts in your face about object-oriented program design that you're not prepared to understand why they're good ideas, right? You won't understand why OO is useful until you've written some bad imperative programs. And then you learn, okay, this allows me to like separate this from that and not step on my own feet. But requiring people to learn them up front is overwhelming, and telling people, just ignore that, you'll just memorize it, you'll understand it later, is like, was anybody ever satisfied with an explanation like that when you were a student? I certainly wasn't. So if the value of these things comes later, let's teach them later when people understand what their point is. So, if you kind of break down like all the garbage that's going on here, there are so many concepts. There's classes, there's access control, there's static versus instance. Oh my God, what's that, right? There's arrays. I don't even know what an object is. Let alone what an array is. Command line, arguments. What's a command line argument? What's a command line? Right? And then, this one, system out, print line, each of those dots means something different. You got a class and you've got a field. What's a field? And it's a final field, but it's actually immutable, but we won't tell you that yet. So, it's a lot. And as it turns out, it's not necessary, right? So, like, the first thing that we can take away is, well, if you're not going to use the arguments, do you really need them? No, you don't need them. If you only have one class, do you really need access control to talk about which other classes can invoke your members? No, of course you don't. Static, well, we don't need that at this point either, right? The compiler can figure out that, this is a class that has an accessible public constructor and an instance main method. I'll do the right thing. Finally, like, this is one of the most common utterances in the first 100 programs you write. Do we really need to make you jump through hoops every time you do it? No, right? So, this is something that we can, and we don't even need to declare the class, do we? Right? I mean, it's like I just want to have some statements that execute and print something on my screen. So, we can boil down the simplest Java program to something more like this. And I know you're all thinking, can you boil it farther? Come talk to me after class. So, this may appear to be syntax and boilerplate, and it is, but it isn't, right? The idea is simple programs should be simple. And we want people to start with simple concepts and build up. Some of us like to write scripts in Java, and these things are hurdles for that too. But the biggest reason for doing this is I read a couple dozen Java textbooks. I didn't read every word, but I looked at the organization of a couple dozen Java textbooks, and I looked at the contortions that educators go through to, as a result of like this being in their face, and it doesn't help people learn how to write good programs. One of the reasons why I think people are teaching Python as a first language is they can introduce concepts, incrementally. You can write your first program in the first 30 seconds and then build up from there. Well, you should be able to teach Java like that too. And you can, but it's the orthodoxy said don't do that. You have to explain everything up front. And so we hope that this will give people a way that they don't have to teach Java differently than they might teach Python. Okay, so wrapping up here, but they said we could have some extra time for questions. I want to talk about the things that are going on in progress now that are, don't necessarily have JEPs, but things that we're working on. So records are immutable. That's great. They have built-in getters. That's great. We don't need setters, but we sort of do need a way to derive one immutable value from another, just like we have things like string.substring. So what does a setter do? It says change this property in isolation. The equivalent for immutable objects is give me a new one with everything the same except this one changed to this value. we don't want people writing code like that. We don't want to say, oh, great, we got rid of getters and setters, but now you got to write withers, right? That would seem like a dirty trick, and that would be a dirty trick. So we don't want to do that to people. So we want to introduce the concept of reconstruction for immutable objects, where you can say, take an immutable object on the left and say, I'm going to make some mutations to its state. This is a very concise way of saying something fairly complicated. When I say p with x equals 0, what I really mean is deconstruct p with its record pattern, get all its components, lift them to variables with the obvious name, and run that block of statements in it. And that means x is initially bound to whatever the x value of the point was, but I can change it to 0. And then at the end, I take the final values of all those components and I feed it back to the record constructor, which validates the invariance and gives me a new point. And so you could think of it as translating, to this, or there's a half a dozen ways, that I could have explained it. But the idea is the stuff in the brackets are just ordinary Java expressions or Java statements. You can have loops and conditionals and method calls, whatever you want in there. It's just that that block is enhanced with some extra variables that correspond to the state of the record and will influence the state of the resulting record. So this is something useful at the use site. It's also useful when declaring methods. So if I have a complex record and I want to declare the complex conjugate, that's the same real value but the negative of the imaginary value. I can just say return this with imaginary equals minus imaginary. And once you know what that means, it's actually a somewhat clearer way to say what you mean. Everything the same except make this transformation. And similarly, if I have my point nested in my circle and I want to change the x value of the nested point, I can just nest these with expressions. Circle with center is center with x equals 0. So records are great. People often ask, can we have some of the goodies for records for regular classes? And of course, this has been on the design plan from the beginning. So one of the things records get for free are these deconstruction patterns. But lots of classes make sense to deconstruct as well. And we can't do it automatically because we don't want to try to analyze what your class does and guess. But you could express it programmatically. So for example, if we have a person class whose fields are first and last name, we have the obvious constructor, we could also declare a deconstruction pattern. Syntax is obviously provisional, but the important thing is this looks like the mirror image of a constructor, doesn't it? The constructor has parameters, first and last in, person out. The deconstructor has bindings, person in, first and last out. The body of the constructor copies values from the parameters into the object state. The body of the deconstructor copies values from the object state into the bindings. So these are mirror image operations. Their use site are mirror images. Their declaration are mirror images. So if we had that, then we could deconstruct a person in the obvious way that we do with records, and we would recognize that records are just a special case of this, and they get one automatically the same way they do constructor and equals and hash code, etc. A little bit farther down the road, once we have deconstructors for classes, I can do the same with trick for classes that I just did for records. What I need is a matching pair of constructor, deconstructor that have an argument list that matches to a binding list. And then I can do the same, deconstruct it, mutate the state, and reconstruct it, which is great because there's more immutable types coming from Project Valhalla. Okay, I think I have one or two left, so we're kind of in the grab bag territory. I mentioned this one earlier. It's a long-standing, annoying restriction that the first operation syntactically of a constructor should be calling the super or calling a this constructor, which is like most of the time okay, but like really annoying some of the time. And the reality is it's a well-intentioned restriction that was just a little bit tighter than it needed to be and can be relaxed so that you can do things like validate constructor arguments in the same way you validate method arguments. So for example, like if I have a class positive big integer, the first thing I could do in the constructor is say, is the value valid? If not, throw, and then go on to do my constructor body. So it's a small feature, although like I said, it was not as small as we thought it was, but it's a nice little improvement. A little farther afield, this is probably one. Actually, this one is there's a JEP for it now. It may come in 23. Is addressing an asymmetry in type patterns between what is a type pattern for a reference type like string s versus a type pattern for a primitive type mean. And to motivate why this asymmetry annoys me, if I have a constructor that takes a double, like JSON number takes a double, I could provide an integer and the language will say, oh, I know how to extend integer to double, no problem, I'll do that for you. I'd like to be able to do the reverse of that when I deconstruct it. I'd like to be able to say case JSON number int x, but currently primitive type patterns are very limited. They mean exactly this type. The reality is that pattern matching and instance of are deeply related to casting, where instance of for a primitive or for any value really means would it be safe to cast this now? And that gives us a very clear semantics of what primitive type patterns mean and eliminate this sort of asymmetry. And again, it's one of those things that you don't notice it until it bites you. And hopefully it will never bite anybody if we get to it fast enough. So this is a pretty straightforward generalization of what's already in the language. Instance of, a lot of people have developed a mental model, which is perfectly sensible, that instance of is a subtyping test because it was only allowed on reference types, and so that's what it meant. But another way to think about what instance of means today is, would it be safe to cast to this type? If you try to cast to something that isn't subtype or supertype of the thing you get an error. That's one way the cast might not be safe. Another way a cast might not be safe is casting along to an int and losing some precision, right? So you lose your high order bits, they just fall on the floor, no one tells you, it sucks. So it would not be nice to be able to say, is this int an instance of byte? In other words, could I cast it to byte without losing any information? And that turns out to be exactly what instance of primitive ends up meaning, and in turn that turns out to be what primitive type patterns mean. So this is one of those things where we did all this pattern matching stuff. It's really cool, and now we're filing down some of the rough edges so that putting things together and taking things apart can look symmetric and be symmetric, and you don't have to deal with those edge cases of I can't do that. So, all right, that's the end of my prepared slides. But like I said, I was promised that we would have time for questions, so hit me. And remember, I can't see anything, so wave your hands around a lot if you want my attention. Everyone wants to jump on the tram as quickly as possible. Sir, in the front.
Yeah, so if we are able to do stuff like the byte thing, if instance of a zero, would it be possible to get to a point where we can just say, hey, why bother with int and long and double? Let's just do number, and then we just deal with what the actual thing is.
Yeah, okay, so the question is, okay, nice progress. You're blurring the distinction between int and byte a little bit. Great, let's do more. Let's just have an abstract number type. Well, let's go back to why we have primitives in the first place, right? Why do we have byte and short and int and long and not just fixed num? And the reason is that for people doing numeric computing, they care very much about how much memory something uses. So you want to be able to have control over the memory layout of what you're doing. And so the primitives aren't going away, but what we can do is make them not so much each their own special snowflake. And this is part of that. The work in Project Valhalla is part of that. Okay, more questions from people I can't see. This gentleman here. So can throw be turned into an expression? So maybe. This is one of those writing code things, right? Because you're not actually making the code that much clearer. You're just typing fewer characters. Maybe we do that someday. We don't generally prioritize things that are purely syntactic like that, but we turn switch into an expression. We might turn more things into an expression. In the red shirt up there. So the question is, you've only shown me deconstruction in conditional contexts, and that makes sense when I'm doing something polymorphic. But if I have something that I know is a point, and I just want to deconstruct it, and I don't want to say if because I know it's going to succeed, is there a way to imperatively deconstruct it? That's your question, right? Yeah. So that is something that is on the roadmap. That we haven't figured out exactly what the syntax of that looks like, but it makes sense to be able to effectively assert that a given pattern is going to match, have the compiler type check that your assumption is correct, and also deal with stray runtime values like null. So even if you're deconstructing something with point, something that is a point, and you deconstruct it with the point deconstructor, you still have to deal with a null case, but you may not want to have to deal with that explicitly. You might be willing to let it throw if that assumption is violated, the same way we do with unboxing now, right? You can assign an integer to an int, and if it's null, okay, we just throw. So yes, on the drawing board. Ask me again next year. All right, more questions. This gentleman here. Yeah. So the question is, will we ever have lambdas in annotations? So the restrictions on annotations right now, they seem very ad hoc. You could have, strings and primitives and enums and arrays of those things and other annotations and frogs and lizards, but nothing else, right? And the secret decoder chart of where did that set of restrictions come from is it has to do is what's representable as constants in the constant pool. So there's kind of a hint there that the stuff that are parameters to an annotation should be data, not objects, not behavior. However, so I'm going to say no on lambdas. I'm going to give you a definitive no, that won't ever happen. But as a consolation prize, it might be possible to do method references there. Because method references are symbolic data to behavior. It's not that hard. It's very messy. There's like 19 layers of gunk that you have to plumb through. So the implementation would be very annoying, but it's doable. Okay, question in the middle here. I'm not sure I'm following what you're asking for. Do you want to be able to overload equals, or is it you
An equal that doesn't accept any object, but only
okay. Oh, this is in the declaration of the equals method, right? So could I declare equals with a different signature? So conceivably we could do that. It's messy. It's pulling a library idiom into the language and requiring the language to see this, recognize this as really a macro for this other thing and generate this other thing. It's not the sort of thing we like to do. We would prefer that you override the equals method from the from the object class. So it's a thing that could be done, but it feels like it's on the wrong side of the lever. I think there was a question in the row behind you. Yes, in the black shirt.
is there any plan about improving serialization?
You had to bring that up, didn't you? So the question is, what are you doing about serialization? You talked about it last time at Devox. What have you been working on? You've been sitting on a beach, right? That's your question. Yes, we are still bashing our heads against that problem. I was actually just talking about it with my colleagues in the hallway right before before this talk. So yes, still on the drawing board. Ask me again next year. All right, let's take one more and then we'll wrap up. I thought I saw there's one over here.
In the beginning, you said that your Java code of 25 years ago is still running today. I don't really agree with that because I started with Java 1.0 and somewhere around 1.2, 1.3 was this renaming of the swing package.
Yep.
And now we have the renaming of the servlet package, which is causing hell everywhere. Are there any other of these things that are going to be renamed as we wait for 2011?
Yeah. So the question is, you said Java code from 30 years ago still runs, and that is true of 99% of the Java code written 30 years ago. But I have a counterexample, so you're wrong about everything. Which was the counterexample was the renaming that was done in 1.2 of the swing, some of the swing classes. We learned from that episode, and we got more serious about deprecation, and we in later years got even more serious about deprecation. So we're very careful about doing those things. Will we ever do something like that again? I can't say never, because like future you will come tell me how inconsistent I am, next time. But we try to be very careful about not doing that with public supported APIs. For internal APIs or implementation details of existing JDK classes, we feel free at any time to change these things. And that will break some libraries that are cheating, and that's going to be a problem for them. I talked about that in the keynote, how we have to get to a point where the libraries that do what they have to do on an older version and then something changes on a newer version are going to have to deal with both versions. But we're extremely careful about how we do that because we understand there's umpteen billion lines of Java code out there, and anything that people can do, they have done. So we do understand that. All right. So thank you very much, and I will see you next year.